And the guys there wanted in person. They wanted to meet me, but they wouldn't fund the flight over there. They paid for the hotel, but they wouldn't pay for the flight. Like, okay, fine. And I was in a bind.
Oh, Chicago JavaScript. Everybody good night? Did everybody get something to eat and drink? That's all provided by ThoughtWorks. Let's give them a hand. And why are you doing that?
I'm sorry, what?
And why are you doing that?
Doing what?
Giving us all this stuff.
Because we love hosting these events and we have plenty of space to share. So I hope you are all enjoying the Qdoba. If you haven't already figured this out, there's a big vintage cooler back there full of beverages for you all. But I'm Jeremy McNay. I'm one of the ThoughtWorks recruiters here. Those of you who do not know what ThoughtWorks is, we are a 25-year-old custom software company. We're tech agnostic. We are a global company. And we are growing quite a bit. So my team, we're looking to hire several hundred software engineers this year at all levels and data engineers. So if anybody wants to talk to us or anything at any point, cool. Otherwise, enjoy the meetup today and enjoy the food. Okay? Thanks, everyone.
Thank you. That reminds me, by the way, I'm Justin Love. I've been one of the organizers of this meetup for a long time. I also have Justin Meyer, who's one of the original founders of the group. You may also know Jankar, who has been helping out a lot behind the scenes. He has unfortunately moved to Dallas. Maybe we'll help out a little bit, but if anyone is interested in helping us find speakers and locations and run events, please let us know. I've been doing it long enough. I'm a little bit burned out, so I kind of like to step back. Justin's really busy. Jankar's in Dallas, so we would really, if anybody has any interest in helping the organization and helping us pick topics and kind of guide where we're going next, I'm really interested in talking to you later.
Yeah, I could add from my personal experience starting the group 10 years ago, I think, maybe something like that. It was very helpful and transformative for me to engage the JavaScript community. Right, I learned so much by reaching out. I played Counter-Strike with Brandon Ike. I've known that as a guy who created JavaScript. We've had remote talks from people who big jQuery contributors and things like that. I know a lot of the JavaScript people actually in Chicago JavaScript community. It's been great and really rewarding. I would love to keep doing it all the time, but I run a business. It's very hard to do that and manage this. But if you are, I think it's a really great thing for someone who kind of wants to focus on the community side of JavaScript development, learn a lot there. Email this contact the organizers on the meetup page to send me or Justin an introduction email, even if you want to help just a little bit, just to be like, hey, there's a meetup 6 months from now. I want to go find a speaker, and I'm going to go email people that maybe you follow in JavaScript. Actually, what was her name? Tanya something? The girl who wrote React's introduction guide. I emailed her just the other week, asking her to come give an introductory talk on React. So even if you want to just help plan a few of the meetups, that's still a big help. Track down speakers and things like that, find space, make sure that the space and the time and everything is ready. That would be big help. So please help. We need it.
Yeah. All right. So meanwhile, we do have a topic and everything's still running smoothly. We just like some help. And today we have for you David with Generative System JavaScript.
Thanks. My name is David Altenburg, and I work at Inventables. We're a smallish company that makes desktop carving machines, and software to drive those machines all runs on the client. It's written in JavaScript. The stuff I'm going to talk about today came out of some of the work that I did there. So, generative testing, and we'll be talking about it specifically in JavaScript. But in general, just by show of hands, how many of you are familiar with the concept of generative testing, like what that is? Has anybody done any work like writing generative tests? So I'm going to cover what this is, why you should use it, and I'm going to go through some real-world examples of the workflow that I use. I'm still new to using it, and so I'd love to hear from anyone who has used it about the workflow that you use. But I'll show you how I've used it to find some bugs in some actual code that I've written. So to talk about generative testing, I want to contrast it with what we normally think of as unit testing. And for purposes of this talk, I'm going to refer to the traditional style of unit tests we write as example-based tests, because that's kind of what we're doing. Is we're coming up with examples of input that we might feed to our code. We feed it into the code, and then we check the result to make sure it matches. There's a lot of frameworks that we use for that. Like the examples in this talk are going to come from Mocha, but the framework I'm using actually works with a lot of the JavaScript frameworks out there. So like if you prefer Jest or one of those other frameworks, it works with that as well. To start out at the beginning, I want to walk through a very basic test for some very basic code. So this code right here, we're creating a function called add that does nothing more than adds two numbers together. It's trivial. It should be easy to test because we know what it does. So let's look at how we might write an example-based test for that code. So this is using the Mocha framework. If you're not familiar with that, this stuff at the top is like boilerplate for the framework that defines our group of tests and the individual tests within it. But the meat of the test is these two lines here. So we give it some example code, or example inputs, the numbers 2 and 3 in this case. And then we make sure, or we feed that into the code we're trying to test, the function add. And then we make sure that the result is what we expect, so that it's 5. It's a trivial piece of code, it's a trivial test. Let's look at what happens when we run it. We see that it's passing. It gives us the suite name, it gives us the test name, tells us that it's passing and how long it takes to run. This is all exactly what you would see on the command line. So to contrast this, I'm going to show you what a generative test for the same code would look like and walk through what it's doing. So we have the same sort of Mocha boilerplate at the top where we group the tests. And here, we're using the number check because the framework that we're using in this talk is a framework called checktest.js. And it comes out of a library that was written in Clojure that was inspired by a library that was written for Haskell. Fortunately, you don't need to know Haskell or Clojure in order to use this. They're great languages, they're worth learning, but you don't need to know anything about them in order to use checktest.js. So we're saying that the test is going to check something. We give it a name. And then there's these two things up here, gen.int and gen.int. These are what's referred to as generators, and as you probably inferred, that's related to why it's generative testing. What they're doing is they're generating inputs for our test. And as you can probably guess, we're telling it that we want to generate integers for the test that we're running. We then give it a function to run the test, and it takes as input those generated values. We don't know what A and B are going to be. We know they correspond to these generators, and we know that they're going to be ints. When we get into the meat of the test, we know that A and B are ints, and we're going to add this in two ways, one with the operator and another with the function we're trying to test, and make sure that they're the same. We don't know what these are, but we know that they're ints, and we know that we should be able to add them together. So this is really what generative testing is. This particular test isn't all that useful because the code is not all that useful, but I'll go into some more detailed examples of, and more sophisticated generators after this. So what happens if we run it? It looks similar to the other test suite. And in fact, using the Mocha integration with testcheck or any of the other integrations, you can mix and match these types of tests. So I could have some unit tests or example-based unit tests and some generative tests, and it'll run them all together and it'll report on them just like the normal test. And this looks very similar to the output of the other test that we ran, with one exception. And if you noticed it, kudos, because it's kind of buried in there. but this took 30 milliseconds to run. Whereas if you remember, or if you happen to notice, the other test took 6 milliseconds to run. So this is a lot longer. But why did it take longer? Because it was actually running a lot more tests. We gave it that generator, and what it did is it used that to generate a whole bunch of tests with inputs that met those criteria. And it ran them all. And because they all passed, it considered the test as passing. Doing that takes more time, but it also is covering a broader range of inputs. Like, what happens if one of these fails? If you remember that add function, it used to just add two numbers together. Let's modify it a little bit to force it to fail. So here, anytime A is greater than the value of 2 times B, we're just going to hard code -1. So for some inputs, it's going to return the right value, and for others, it's going to return -1, which won't be the right value. So if we rerun our test, here's what we see. We see a failure. It looks like any other test failure in Mocha, except it gives us a little bit more information. So it tells us which test failed. And then we have this line here, check failure. And then it gives us these numbers. These numbers happen to be the inputs on which the test failed. And then finally, it tells us the assertion that triggered the failure. So the generative test generated a whole bunch of sample inputs and ran them. And when it generated -1 and -1, it gave us the wrong value. So we know that it doesn't work for those values. One other thing that might be worth noting is this test failed in 16 milliseconds. The test that passed took 30 milliseconds. This failed a lot faster than passing it, because once it encounters a failure, it's not going to keep running. It knows that this fails, therefore the entire test fails. There's no point in checking other stuff to see if it passes. With one exception, and this is a detail you don't necessarily need to consider to write generative tests, but it tries to give you the most useful failure message it can, and it does that with a concept that refers to as shrinking. And that's where it takes the input that triggered the failure, and it tries to see if there's a simpler version of that input that will also trigger a failure. And it has some heuristics for what constitutes simpler. Numbers closer to 0 are simpler than numbers farther away from 0. When it comes to collections, it's more intuitive. Like a small array is simpler than a big array. An empty array is the simplest of all. So you can get a failure with that. That tells you something. So it tries to report the simplest failure that, or the simplest input that will trigger a failure. So one thing I want to be really clear about is I like generative testing. It's really useful, and I hope to convince you of that. But I'm not trying to convince anyone that we should throw away the usual way that we write unit tests of examples. Those have a lot of things that they do really well. That's why I hope that you're familiar with that style of testing. It's why it's common, and we've been doing it for a long time. And I want to highlight some of the things that I think really make them stand out, especially in contrast to generative testing. So one is that those example-based tests work really well as a guide for test-driven development. Like when I'm looking at a blank screen and I'm not sure where to get started writing code, I always know that I can write an assertion, and that's sort of the thing that'll start to unlock the shape of that code. And so by writing that, I get a sense of what code I need to write. I get a sense of like what's a basic test that can pass, and that kind of gets the ball rolling. So a lot of us call that test-driven development, or you might hear behavior-driven development. And example-based tests work really well for guiding that workflow. Another thing they do really well is they serve as really good documentation for developers who might come along and wonder what your code's doing. Or yourself, if you're coming along and you're wondering what the code you wrote a long time ago is doing. Like, as humans, we think in examples. This talk is filled with examples. Trying to explain concepts, we use examples. And those example-based tests help us understand like what's the purpose of this code. Sometimes it can be more detailed, like what will it do in this weird corner case that I thought of? And hopefully there's a test that does that. And that's another thing that example-based tests can do really well, is you can codify any of the weird corner cases that you know about. And that way you can make sure that the code works for them, but also you have a record that you've thought about those cases, and if it stops working for those cases, you know that the test is going to fail. But example-based tests, even at the unit level, don't cover everything. And that's where I think generative tests can help fill in the gap. So even though the examples in those tests can serve as documentation, it's not complete. If you don't have every corner case, then a developer who comes along can't look at the tests and figure out what the code will do for those. And if it doesn't do what the developer thinks it should do, it doesn't tell them whether your intention was what the code does or whether it's something you didn't think about and maybe a bug. Additionally, you as I kind of alluded to, like corner cases aren't necessarily all going to be covered. So as programmers, we start to get used to the sorts of corner cases that we think we should test for, like nulls are a big one, empty strings, really long strings, really big numbers, negative numbers. But sometimes like the weird inputs aren't always obvious. And the example I'm going to show later in this talk demonstrates that. So it's a sequence of numbers. It doesn't look like anything special, but it happens to really break the code under test. So enter generative testing to try to fill in some of those gaps. In addition to just forcing us to think about what the code should do in specific examples, it forces us to think about what it should do in a more general case, what it should do for the range of input that's going to be generated. And it codifies that thinking into a test so that it can keep running, so that developers can come along and know this is how it's been thought about, and they know that it'll work for those. And it does a really good job of catching bugs for those corner cases that a developer might not think about. The downsides and the reasons why I think generative testing hasn't really taken hold the way example-based testing has, the most obvious is that it's harder to write these. It requires more thought. We have to think about not just what are some inputs that might work, but what are the rules that describe all of the inputs that might work? And that's not easy. The example I showed of adding two numbers together is easy, but for real-world code, where we're working with real-world data, figuring out how to generate valid real-world data without wasting a lot of time dealing with data that is not valid, that takes real work. The upside is that work is actually valuable because it helps us think about our code better. And as I alluded to in showing the output of running these tests, generative tests do run more slowly. That can add up over a big test suite. 30 milliseconds isn't a very long time for one test, but a real-world test suite can have thousands of tests. And a fast-running test suite is a nice thing to have. So we don't want to take for granted that runtime.
I think it's faster than the regular one. For example, you did.
So the very first example that I gave was not a generative test. That ran in 6 milliseconds. And that was the fastest of the three. The passing generative test ran in 30 milliseconds, and the failing one ran in 16 milliseconds. And that was for a pretty trivial test as well. So with when we're generating more complex inputs, that time can actually go up quite a bit. And then finally, you've probably heard that saw about how testing can prove the existence of bugs, but it can never prove the absence of them. No matter how many tests we write, unless we're testing the universe of inputs that could possibly be given, there could still be bugs. Generative testing doesn't fix that. However, what I hope to demonstrate is that it does take massive steps towards closing that gap, and for practical usage, while we're not proving our code is correct, can be very helpful at improving that confidence and finding those bugs.
Would you say that generative testing is best used for synchronous code and just methods or that just return us a known value rather than asynchronous code? Or
That's a good question. And I don't know if I've thought about it enough to give a good answer. It would definitely be a lot harder, but everything's harder with code that's not synchronous. So I don't know if there's anything special about generative testing versus testing any code that is non-deterministic is always difficult. So I'm not sure if it's even more difficult with generative. I haven't put on that.
Because it sounds to me like this generative, especially this library that you're using, is that it gives you all of these potential inputs that you can quickly run without you having to think of like, oh, what are some of the edge cases? It just throws a whole bunch of inputs at it, and that's why it takes so long.
Yes, that is correct. That's exactly right. So to write these tests, we need a way to generate the inputs, and testcheck gives us a bunch of ways to create generators, and I'm going to go over some of that. Not all of them, because there's a lot, and the documentation for testcheck is pretty good. But I hope this will help you get started. So I'm going to categorize them into basic, parameterized, and more sophisticated. These are my categorizations. You won't find them on like testcheck's documentation. They're kind of arbitrary. So this is an example of what we might see in the command line if we fire up a node REPL and play around with testcheck generators. And I hope this will show a little bit of what they can do. So we already saw gen.int. And gen is an object that we import from testcheck. Sample is a function that we import. Sample is really helpful in playing around with these, and what it does is it invokes that generator several times to give us some sample output from that generator. So gen.int, as you'd expect, returns a bunch of ints. Some are positive, some are negative. There's a lot of zeros in there. There's a gen.negint, and I'm sure you can guess what that does. And then there's a parameterized int generator, int within, so it'll generate ints within a range of numbers. There are a whole bunch of others. There's like pos int and a few more that you might expect as well. And in fact, has generators for most or all of the sort of built-in JavaScript types. So here's some examples of how you can generate strings. The basic gen.string generator generates a whole lot of strings of various types. If we want ASCII, there's an ASCII string generator. There's a parameterized generator for generating substrings of a string that you give it. There's a way to generate collections. So arrays, the array generator takes as an argument another generator, because we need to tell it what sorts of things we want to put into that array. So here we're saying we want to generate arrays of ints by calling gen.array with the parameter of gen.int. And then there's an object generator, which and we use a lot of objects in JavaScript, and this is where we start to get to more sophisticated and complex generators. And to help us out, it has a little bit of parameterization. So this object generator, I'm calling it with parameters to give it a generator for the keys of the objects, another generator for the values of the objects, and then this constraint saying I want every object to consist of exactly 3 key value pairs. And so it generates a whole lot of objects that meet that constraint. This is an optional constraint, and there are a few other constraints you can give as well that are fairly well documented. And then for more sophisticated objects, it gives us some other tools that allow us to compose generators to meet whatever sort of rules we want to establish for that input. And these are just a sampling of some of the ones it gives us. So one of takes 2 generators, and we don't know which it's going to return each time it generates a value. Or it actually takes an array of generators. It could be some arbitrary length. Gen.return always returns the same thing. Probably not too useful by itself, but in combination with other generators, it can help create the sort of constraints that the data you're working with should obey. And to go even further, the generators have filters. So this such that generator on the int generator lets us generate integers that meet this, this logic right here. These types of generators take a lot longer to generate matching input, as you might imagine. So with that overview of what generative testing is, what the generators are, I want to walk through a real-world example. So this is kind of what got me excited about this type of testing, and when I tried it, it immediately found a bug for me. And I'm going to walk through the bug that it found and how the workflow I've evolved since then to help find those bugs. But to do that, I have to take a little bit of a tangent into computer science, because the library I was working on is a data structure known as a red-black tree. I was writing one for my own use. I was kind of surprised that I couldn't find one in JavaScript that met my needs. But I want to explain what that actually is. So a red-black tree is a type of data structure, which means we can put a lot of data into it. Specifically, we can put key-value pairs, just like a JavaScript object. And each key will be present at most one time. So if a key is already present in one of these things, and we put another value with that same key in there, it will replace the key that's already there. The thing that makes red-black trees useful over just plain old JavaScript objects is that they're in sorted order. So you can kind of see that here. Like, the number to the far left is the lowest, the number to the far right is the highest. So they're actually a structure. So there's one special value, specifically root. And each root contains exactly 2 children. Because of that, we refer to this as a binary tree. The root in binary tree diagrams is always drawn at the top as well for some reason, even though it's counterintuitive. And the rules that binary trees obey is everything to the left is going to be less than the thing that it's rooted at. 1 is less than 3, 1 is also less than 5, all of these are less than 5. And all of these are greater than 5. That's how we know the order. And because of that order, we can walk through this thing in order efficiently. We can find out what are adjacent values pretty efficiently. We can do a lot of useful stuff if we care about the positioning of that data relative to each other. And then further, the red-black tree is what we call a balanced binary tree. So to explain that, I'm going to show you what an unbalanced binary tree looks like. So in a lot of binary trees, the branches could be widely varying in lengths. This one's perfectly balanced. So why do we care if it's balanced? If we're trying to find a value in a balanced tree, it's if we know that the branches are all about the same length, we know that none of them is extraordinarily long. And that matters because the amount of time it takes us to find a value, or to insert a value, or to delete a value in this tree is related to the length of the branch. So, as an example, let's say we wanted to find the value 6 in this tree. How would we do it? We start out at the root at 5. We know that 6 is greater than 5, so we go to the right. We know that 6 is less than 9, so we go to the left. And now we found 6. We didn't have to look at any of these other values in the tree. We only had to look at 5, 9, and 6. What if we're trying to find 7 in the tree? It's a similar thing. We start out at 5, we go to 9. Then 7 is less than 9, so we go to 6. And 7 is greater than 6, so we look at what's to the right of 6, and there's nothing. So we know that 7 is not present in that tree. Now let's consider an unbalanced tree. What if we wanted to find out if 11 is present in that tree? We would have to walk all the way down this chain. That's a lot more comparisons. If you're familiar with big O notation, you're probably familiar with this. We would say that an unbalanced tree, in worst case, could be O of n, whereas a balanced binary tree is going to be O of log n for insertions, deletions, and updates, or retrievals. That can make a big difference when you're dealing with a lot of data. In practice, a lot of people will use unbalanced binary trees because the randomization will sort of make sure all the branches are more or less the same length. But if you're dealing with data that happens to be sorted in different ways, that can cause it to skew in ways that don't work very well. So that's where a red-black tree fits in. It's a way to allow us to keep that tree balanced. And the way it does that is by being constrained to a bunch of rules. So the first rule is that every node is red or it's black, as I've indicated here. The root is always black by convention. All of the leaves are black. And here, I don't show the leaves in most of the diagrams in this talk for just to keep the diagram simpler. But anytime it's not shown, it's a null, and the leaves are null, those are always considered black. In addition, we say that every red node has 2 black child nodes. So in other words, we'll never have a red node with a red child node. Any red nodes, or any path of nodes, is never going to have 2 reds right next to each other. And finally, every path from any node to its descendant leaves contains the same number of black nodes. So these 2 rules in combination with each other mean that the longest path in a red-black tree is going to be at most twice as long as the shortest path. I'm not going to, like, that may or may not be clear. If it's not, you can trust me on that. There are proofs that I'll actually reference at the end. I'm not going to walk through the proof now. But mostly, I think you can see that if the number of black nodes is the same, and one is longer than another, then the difference must be in the number of red nodes. But if you can't have 2 red nodes in a row, that sort of restricts how many red nodes you can actually have. So to demonstrate my test workflow, I'm going to walk through an operation that's part of a red-black tree insertion, a test for that, and a bug in that. I'm not going to go into all of the code that we use to do this because we have limited time, but we will see a little bit of it. So let's talk about how we do insertion in order to obey those rules that I laid out on the last slide. So right here, this is a valid red-black tree. It's not perfectly balanced. You can see that this is a little longer on the right than on the left, but it does obey those rules. What if we wanted to insert the value 16 into this tree? We would start out at the root, 9. We go to 20. 16 is less than 20, so we go to the left. We go to 15. And we look at the right of 15, and we can see that there's nothing there. That's where 16 belongs. So we put it there. We insert nodes as red, and now it's in the right place. However, this tree no longer meets the red-black tree criteria. And specifically, the 15 to the 16, like the 15 should have 2 black children, not a red child and 1 black child, which is the null that I'm not showing. So we have to do some fix-up of this tree. In this case, the fix-up is pretty easy. We just do a little bit of recoloring. So we take the 15 and the 30 that were both red, and we change those to black. And then we change that 20 up there to red. Now this meets the rules. It's not always so easy. We don't always get away with just recoloring things. Sometimes we have to do some rebalancing. That's how we maintain the balance of a red-black tree. The colors of the nodes help guide us to tell us what types of rebalancing we need to do. So to demonstrate that, let's consider inserting 17 here. We would go from 9 to 20 to 15 to 16, and the 17 would go to the right of 16, as it does here. Again, we're no longer meeting the red-black tree rules, so we have to do some work to clean this up. We can start out with some recoloring. So we swap that, so we do a color swap between the 15 and the 16. But we still don't actually meet the rules. In particular, this path right here, from 9 down to 16 and all the way to a null somewhere, has more black nodes than the path from 9 to 4. Additionally, the path to yeah, I think that's right. I might have misstated that. But right here, we're not exactly balanced. Oh no, I take that back. It's not the number of black nodes. The problem is the 15 has a black node here, so we could have a shorter path to the null here than we would to the null that's the child of the 16. In order to do that rebalancing, we have to do something we refer to as rotation. In particular, this is going to be a left rotation on this 15 node. So if you can imagine us like taking these 3 nodes, detaching them from the tree, rotating them so that the 16 is now the root of those 3 nodes, and reattaching it to the tree, that's what we're going to do. And so that's what we end up with. writing the code to do these rotations is pretty straightforward. It's really well documented in a whole lot of places, but it's really, really tedious, and it's kind of hard to think about. Like, even in the last slide, even though I wrote code to do this, again, like, it's easy to get tripped up in thinking about things. And there's a lot of places to create bugs in doing this sort of thing. So this is a great candidate for something that'll generate a whole lot of tests for you to find those places where you might get tripped up. And that's exactly what I did in the first implementation I wrote of this. So I'm going to go over like my workflow for writing these tests. I find that the easiest thing to do to write a test for code, even if I'm going to ultimately be writing a generative test, is to start out with a basic example-based test. So there's no generators in this test. Instead, we're doing some sample inputs. What we're doing is we're inserting into a tree the input with a key of 3 and a value of 42. Then we check to make sure that after we've done that insertion, it contains returns true. Put returns false because that value wasn't already in the tree. It returns whether or not you're inserting or replacing it. And then finally, to make sure that we associated the correct value with the correct key, we try to get the value for 3 out of the tree, and we insert that is what we insert that's what we insert. So after I write this example-based test, then it's time to think about how to generalize that into a generative test. And that's what this is right here. So we have 2 generators, and they're both arrays. They're both arrays of ints. I've named them included stuff and all stuff. The idea is I'm going to go through included stuff and insert everything in included stuff into the tree. Here, for simplicity, I'm setting the key and the value to be the same. So we can sort of ignore that it's key value and just pretend that we're only concerned with keys. I'm going to insert that. Then I'm going to go through all stuff and see what in all stuff is contained in the tree. If it was an included stuff, then I should have inserted it, so it should be there. And if it isn't, then it shouldn't be there. So presumably, in a lot of cases, there's going to be some overlap in the generated values in included stuff and all stuff. And that overlap is what we're going to see for this line. For things that are in all stuff but not in included stuff, that's what we're going to see for this line. So I run this test, take a look at the output, and it fails. There's some problem with the code, or at least my understanding of it. So test check gives us the inputs on which it failed. And this is actually the simplest, or it couldn't simplify this input any further. So I want to walk through exactly what it's telling us, because this can be a little tricky to read. There's 2 values in here, and each value is an array. So it's saying that the first array, the included stuff, -1, 2, 3, 0, and 1, and the second array of all stuff, an array with just 0, were the inputs that caused the test to fail. But looking at these inputs, I mean, I see that 0 is included stuff. So that implies that when I checked 0 in all stuff, that it wasn't there. I think I inserted 0, but it wasn't there when I checked to see if I had inserted it. And in fact, this is the simplest input that causes this failure. If I remove the 1 from that array, the test passes just fine. But how can it be that we inserted 0 and we couldn't find 0 in the code? And where do we then look into the code to find this problem? Well, with these types of failures, what I found that's helpful in debugging them is to take that failure and then codify that into an example-based test. So what I do is I take all the code from my generative tests and I remove the generators. Instead, I hard code some values to the inputs that caused the test to fail in the first place. So hopefully these inputs look familiar to you. And this is just that generative code, except this stuff is hard coded. And then there's one other line. I use console.log of the string representation of the tree. So I can see what's actually going on in the tree while it's inserting stuff and then when it fails. The idea here is things are no longer being randomly generated. So I can run this test over and over again, get it to fail over and over again, set breakpoints, put in log statements, whatever. Reproducibility is the way we solve bugs, and this makes it reproducible. So toString returns a string representation of the tree. It shows every node in there, along with the coloring, along with the values. For this talk, I'm actually, I've taken that string representation and turned it into diagrams to make them a little bit easier to read. But as it loops through there, it dumps out the string representation of the tree at each step. And the last step, before the test fails, this is what the tree looks like. So if you remember, we're trying to find the value 0 in this tree, and we didn't find the value 0, and so the test failed. So let's see what would happen if we tried to find the value 0. So the way we find stuff is we start at the root, we look at 2. 0 is less than 2, so we look at -1. 0 is obviously greater than -1, so we look to the right. We see that 3 there. 0 is less than 3, so we look to the left, and it's not there. But also, you may have noticed there's something else messed up about this tree. That value 3 is in there twice. And as I said before, each value should be present in the tree only one time. Technically, each key should be present only one time. But here, the keys and the values are the same. But also, if we go back to the test, it's not like we even tried to insert 3 twice. We inserted it once, and somehow it showed up here twice. How did that happen? You can figure that out. There's a good chance that we found our bug. So let's look at the representations of the tree's earlier steps in the test. This is the last representation, or the first representation that had the 2 3s. So something right up until this must have triggered this bug with the 2 3s. This is the representation right before that. So we inserted a value, probably a 3, to this, and somehow it led to this with 2 3s. We can figure out what's going on there. We probably found the bug. So how could that have happened? Here's what should have happened. We have this tree rooted at -1 with a child of 2. We try to insert a 3. But now we need to do some fix-up because it no longer meets the red-black tree property. So we do a little bit of node recoloring, and then we do a rotation, a left rotation on -1. And this is what we should have ended up with. Instead, what happened was this. We had the 3 inserted, we needed to do some fix-up, we did some node recoloring, and then when we did a left rotation, somehow we ended up with these 2 3s. So let's look at the implementation of the left rotation, because that seems to be where the trouble lies. This is the implementation of left rotate. I'm not going to walk through all of this line by line, because it's not necessary to demonstrate what's happening here. Also, as I mentioned before, like the code to do this, it's not hard to write. It's well documented in a bunch of algorithms text. It's just really tedious. There's a lot of ways to get it wrong. There's all these lefts and rights, and if you mix those up, that's a thing. There's also a function called right rotate that's, as you imagine, a lot like this, except a lot of stuff is swapped, but not everything, so you can't just reuse the same code or anything like that. There's just a whole lot of this nested logic that's really nasty and really hard to actually factor out to get right. So for this code, we call it on X, which is like the top of the node set that we want to rotate. And then it assigns right to the right-hand child of that. And then it does some reassignments to actually do the rotation. I'm not going to go through those reassignments. I'm going to kind of skip to the end and tell you that the bug is actually on this line right here, where we look at the right-hand child of the X node and we assign to its right-hand child whatever the child of the Y node is. What this should be is looking at the left-hand node of the Y node. So I hope that it's kind of clear that by doing the wrong assignment, by pulling this 3 off of the 2 and putting it on the left of the 1, that's where that extra 3 showed up from. because we never removed this from the 2. From like the y node, we never reassigned its right child here. We just reassigned the right child of the x node. So if I fix this up, I rerun the test, I end up with this, and test works. It helped us find a bug in some hairy code. I want to go back to that input code again, though, because the one thing I think that really demonstrates what I like about generative testing. This sequence of stuff, -1, 2, 3, 0, 1, there's nothing that looks special about it. Like if you asked me to find code that would have exercised that bug, I don't think I would have been able to think about it just, reading about it. Especially since I didn't know the bug was there in the first place. This let the computer find it. Like it generated a whole lot of inputs, and most of them worked fine. This one didn't. And I had actually written some unit tests for this code before I threw generative test at it. I didn't realize it was broken. I'm sure I would have found out about it in another context. Like when I was actually trying to use the code to do something, it's so much better to find it when you're testing. So I want to recap the workflow that I use for working with these generative tests and finding bugs within them. So I find it easiest to start with an example-based test, because those are easier to write. They're easier to think about. It's a good starting point. And then I usually write the code to make that test pass. Then once I have this working code, I generalize that example-based test, or maybe a group of example-based tests, into a generative test, or a property-based test. And I run that. And if that fails, to debug the failure, I'll take the failed inputs and I'll hard code those into an example-based test. And then I can run that test over and over again to get to where the bug is. Once I fix the bug, that does raise the question of, do I delete that example-based test of the failing inputs? And that's sort of a judgment call. Like, are those inputs really special? Is there something intrinsic about that being tricky and I want to really capture that? Or did I just make a typo that's not likely to be made again by a coder, and I'm going to rely on the generative test to catch it if it were to show up again? Like, I think that just really depends on the situation. As far as working this workflow into like a bigger testing workflow, like continuous integration, working with like other team members, that's something I'm still figuring out. And there's like a couple things to consider with doing this. And I'm still not sure the best way to approach them, but I have a few thoughts. So one is the test run time. As I've said, like these generative tests take a lot longer to run than example-based tests. If you have a really big test suite, that can matter a lot. So it does raise a question of like, do I want to write a whole lot of these, even if it's going to make the tests a lot longer to run? How much time should I spend trying to performance tune my tests so that they can run faster? Which in this case would be performance tuning the generated inputs to make sure that they don't take too long to generate. I'm still not sure the answer for that. It seems to me that the return of finding bugs faster is worth the extended runtime, especially if we have a beefy continuous integration environment that can run them quickly. But that is a concern. Another one is the reproducibility of these tests. Because the computer is randomly generating inputs, those inputs change from time to time. So if you use continuous integration and you ever have that situation where like you have a test that it passes 99% of the time, but like 1% of the time it fails, like how fun is that when that happens? And unless your team is well disciplined, sometimes they get into a habit of seeing that there's a test failure on the continuous integration server and just clicking that rerun button. If you're in the habit of doing that with generative testing, I don't think it's going to go too well. Because in this case, those failures could be real failures. It's possible that generator is not going to fail all the time. Sometimes it will generate inputs that fail. So that sort of habit I don't see as being really compatible. And that habit, I've been on teams, it's hard to break. It's really hard to have a comprehensive test suite it never has false failures. But I think it's worth it, and especially if you're going to use these types of tests, I think it's definitely worth that effort. If you really want to eliminate randomness from your test suite and you're using generative tests, it does have a way for you to specify the random seed that the random number generator is going to use. So in that case, even though it's random, it'll be the same random values every time. But I think that takes away from a lot of the value of using these tests in the first place. Not all of it. And it could be that you run them a lot until you're confident, then you hard code that random seed. But I'm not quite sure why you do that instead of just making sure that your code is resilient for all the inputs that might get thrown out. So that's it. These are the references that I have. So the library I talked about here is called testcheck-js. I didn't write it. I haven't actually contributed to it. I just really like it. I found it easy to use, and it's well documented at that site right up there. The library, the red-black tree library I described, it is called Balanced Tree, and it's available there. We're using it. It seems to work really well if you need a balanced tree library, or if you're curious about the implementation. You can look at it there. It's available on NPM as Balanced Tree, I think, as well. And then the reference I use for writing it is a book I really recommend if you found that part of its talk interesting, you'd like to learn more. Introduction to Algorithms is a really good algorithms book that goes into a lot of detail. It's very well detailed in how red-black trees work. It's one of the few books I saved from college that I still refer to regularly. And a lot of people refer to it as CLR for the first names of the three authors. I'm not sure why Stein doesn't get credit there, but that's where all that came from. And that's it. I'll be around for questions, and yeah, I'd love to talk to you about how you're testing. And if you've ever used anything like this, I'd love to hear about it. But if you also want to talk about how it might fit into your workflow, I'd be really curious what your thoughts are on that. Thanks.
All right. Good night, and thanks for coming out. And yeah, if anybody thinks you might want to get involved in the group, please let us know.
That was good.